I think your instructor also talked about a couple of other features that can make the difference between whether you are strong or weak field. So for example, let's compare, say, cobalt 2+ and cobalt 3+. Let's say we have cobalt 2+, and we know that each of these ligands represents a negative charge. Let's compare that to cobalt 3+. Now, in cobalt 3+, do we expect the ligands to be held closer or further from the center?
Closer.
That's right. Why closer?
Because the charge is like more and it pulls more.
If the ligands are negative, they're going to be strongly attracted to this greater positive charge. So in this case, I'm going to draw all the negatives closer to the center. Now the question is, now that these are all closer, are they going to split the energy by a greater or smaller amount for the d orbitals?
Smaller.
It's going to make a bigger or smaller difference. Now remember that the problem here is that we have a bunch of lone pairs on the cobalt. And the lone pairs don't like pointing directly at the negative charges. Well, in which case it's going to be worse to point at the negative charges if the negative charges are close or far.
Ones and smaller ones because it's too close to each other. I mean, that cobalt 2+ is better. Probably.
Yeah, that's right. So it's worse to point at the negative charges here. So which of these is going to have the bigger energy splitting? Which is more likely to be the strong field and which is more likely to be the weak field?
One more time, question.
Which of these is more likely to be a strong field case and which is more likely to be the weak field case? So for example, let's say we're focusing, so let's say we have some of the ligands, so we could think about the negative charge not pointing towards, the lone pairs not pointing towards the ligands. Now in this case, if the lone pairs are pointing towards the ligands, they don't like it, but it doesn't make that big of a difference because they're still a long way away from the ligands.
Right.
So in this case, you'd only go up by a small amount in energy if you were pointing directly at the ligands. So this would tend to be the weak field case.
So when it's a 3+, it would have more repulsion between the ligands and the lone pairs.
Because they're closer to each other.
Oh,
Remember, the
okay.
lone pairs are on the cobalt.
Might be higher. Okay.
The lone pairs are on the cobalt. They don't like pointing to the negative charges, but it doesn't matter very much if the negative charges are a long way away. But in this case, the negative charges are very close to the lone pairs. So here's where it's really bad to be pointing toward the negative charges. And when it's really bad, there's a bigger energy jump.
Okay.
So this would tend to be the strong field case.
This would be strong field.
And we tried to give an explanation of why that was. This is something you could kind of figure out. You could kind of figure out that the more charged the transition metal is, the more likely it is to be in the strong field case. The more charged the transition metal, the more likely it is to be in the strong field case because it's pulling the ligands closer, so there's a bigger price to pay when the d orbitals are pointing toward the ligands. If the ligands are far, far away, it doesn't really make much difference whether you're pointing to them or not. So there's only a small energy difference between when you're pointing towards the corners and when you're not. So you can make predictions based on the charge on the transition metal. So for example, if we look at our spectrochemical series again, notice that ammonia is a little bit in the middle. So it's a little hard to predict whether it'll be strong field or weak field. And they mention here that ammonia is weak field towards cobalt 2+, but strong field towards cobalt 3+. Is that consistent with what we've just been talking about?
Yeah.
So ammonia is, ammonia here is strong field towards cobalt 3+. In fact, I think that's what we got in our previous example. Remember, we did cobalt with ammonia, and I just told you that was strong field. But that's because that was cobalt 3+. If you did cobalt 2+, it turns out that that would be weak field, because the ligands would be further away, so it doesn't hurt very much to be pointing towards them. Okay. So I don't think you'd be expected to predict out of the blue whether ammonia was strong or weak field, but you should be able to predict how things tend to change as you change the charges.
So based on the charge of the cation, then the ones in the middle, you can more so predict which way they would go towards?
You can predict which way they would tend. Yeah, that's right. On the other hand, if it's far on the ends, for example, if you're far on this left-hand side, say, so cyanide is pretty much always going to be strong field.
Right.
And iodide is pretty much always going to be weak field. So again, I don't think you need to memorize this, but maybe you might just want to memorize the one on the left and the one on the right, since those are the ones that are the clearest.
Even if like we'll have strong field ligand and a weak, we can like for sure say that it's strong field or weak field.
If it's from the far left and the far right.
If it's somewhere in this area,
then it depends.
Then we can
on
look at the cation.
Okay, that makes sense.
Okay. Question here is to predict the number of unpaired electrons. In this compound, let's predict the number of unpaired electrons.
Number of unpaired electrons.
Right.
This is strong. And this is weak. So it still goes up. 2.
What was your answer? Okay, good. So you found the oxidation number. Now neutral chromium has 6 valence electrons because it's in the 6th column. It's good that you're avoiding a common mistake. A common mistake is to only count the number, count the D columns. But we need to count the S and the D columns here. So there's 6. But then if we take 2 away, there's only 4. Now how do we know whether this is going to be strong field or weak field?
Because of the cyanide?
Yes,
So it makes it want to be strong field?
Yeah, strong field is all the way on the left on that, what's it called? Spectrochemical series? Photochemical series? It's all the way on the left in the photochemical, on the spectrochemical series, which means that it's pretty much always going to be strong field, regardless of what the transition metal is. All right, so this doesn't have a particularly big or a particularly small charge, but it doesn't really matter because cyanide is so far to the left, I think it will pretty much always be strong field. In any case, that's clearly the clue they wanted us to use. So we don't need to bother drawing the weak field case, because this is cyanide. And where does the 4th electron go? Down here. It doesn't want to pay this big price of being close to the cyanides. So how many unpaired electrons? 2 unpaired Electrons. Good.